I don't know if you know this, but Mr. Burke, the biology teacher, is a cyclist. Sometimes he rides his bike all the way up to Prescott and back. Let's take a look at one Saturday afternoon where Mr. Burke went on a long 6-hour bike ride. The position or distance his bicycle is from home can be represented by x of t, where x is measured in miles and t is measured in hours. Let's take a look at this function x of t graphed from time 0 to time 6. This function will of course give us the position or location of his bike. Notice at time 1, his bike is 5 miles from home. At time 2, his bike is 16 miles from home. I'm going to say x of 2 is 16 miles. At time 3, his bike is 27 miles from home. At time 4, his bike is 32 miles from home. At time 5, he seems to be headed back home. His bike is now 25 miles from home. I'm going to say x of 5 is 25 miles. And finally, at time 6, he's home safe and sound. Here I'm asked to find the average velocity of his bicycle from time 0 to time 4. Well, the concept of average velocity does not require calculus. I can determine an average velocity without needing to calculate any derivatives. Let's just determine the distance he traveled from time 0 to 4, and then we'll divide by a time of 4 hours. To determine an average velocity on a time interval of a to b, I simply need to determine the distance traveled from time a to b and divide by the amount of time that has passed. So let's see. At time 4, he was 32 miles from home. And at time 0, at time 0 he was home. And of course, 4 minus 0 means he's been cycling for 4 hours. He cycled a distance of 32 miles in 4 hours. His average velocity was 8 miles per hour. Let's see what his average velocity was from time 0 to time 3. At time 3, he had pedaled 27 miles. And of course, at time 0, he was home. And of course, this occurred over a time of 3 hours. I'm going to say during the first 3 hours of his bike ride, his average velocity was 9 miles per hour. Let's find his average velocity from time 1 to time 3. At time 3, he was 27 miles from home. And at time 1, he was 5 miles from home. And 3 minus 1 means he's been pedaling for 2 hours. Well, 22 divided by 2 is 11. His average velocity from time 1 to time 3 was 11 miles per hour. Finally, let's find the average velocity from time 3 to time 5. At time 5, he was 25 miles from home. At time 3, he was 27 miles from home. And 5 minus 3 is a time of 2 hours. Negative 2 divided by 2 is negative 1. From time 3 to time 5, his average velocity was negative 1 mile per hour. But in calculus, we can calculate something known as an instantaneous velocity or instantaneous rate of change. And to do that, we need to determine a derivative. The derivative of the position function x of t is the velocity function v of t. Let me determine the derivative of x of t. I'm going to say x prime of t is 12t minus 3t squared. I can either call this x prime of t or I can call it v of t, the velocity function. We can now use this function to determine his instantaneous rate of change or velocity at any time we want. What was his velocity at time 2? Well, 12 times 2 is 24, and 2 squared is 4, 3 times 4 is 12. 24 minus 12 is 12. At time 2, his velocity was 12 miles per hour. Let's see what his velocity was at time 5. 12 times 5 is 60, 5 squared is 25, 3 times 25 is 75, 60 minus 75 is negative 15. His velocity at time 5 was negative 15 miles per hour. You can see at time 2, he was still on the part of his journey where his distance from home was increasing. His velocity is positive. And you can see at time 5, he was on the part of his journey where he was coming home. His velocity is negative. Let's determine our second derivative so we can calculate his acceleration at various times. The derivative of 12t is 12, and the derivative of 3t squared is 6t. I can say x double prime of t, the second derivative of x of t, or a of t, is 12 minus 6t. Let's see what his acceleration was at time 2. 6 times 2 is 12, and 12 minus 12 is 0. At time 2, his acceleration was 0 miles per hour squared. His velocity was neither increasing nor decreasing. At time 5, his acceleration is 12 minus 6 times 5, or 12 minus 30, his acceleration is negative 18. Now that we have the velocity function and the acceleration function, we should be able to determine if the bike is speeding up or slowing down at any time we want. To determine if it's speeding up or slowing down at time 2, we simply need to look at the velocity at time 2 and the acceleration at time 2. The velocity at time 2 is positive. The acceleration at time 2 is neither positive or negative. The acceleration is 0. The bike is neither speeding up nor slowing down. Let's take a look at time 5. The velocity at time 5 is negative. The acceleration at time 5 is also negative. The velocity and acceleration have the same sign, so the bike is speeding up. The bike is speeding up because the velocity is negative and the acceleration is negative at time 5. Here the function s of t, which represents the number of shoppers at a shopping mall, is given to us in the form of a graph. Let's evaluate s of 1. Well, it appears at time 1 there are 2,000 shoppers in the mall. We can also evaluate s of 3. It appears at time 3 there are 4,500 shoppers at the mall. When we're asked to evaluate s prime of 1, we're being asked to evaluate the rate of change at time 1. And recall that the rate of change of a graph is the slope of the graph. So we're being asked to determine the slope of the function when time equals 1. And notice that this portion of the graph is a line segment. We should be able to get the slope of this line segment. This graph goes up 2,000 over 1, up 2,000 over 1. So like s of 1, s prime of 1 is also 2,000. However, the units should be shoppers per hour. At time 1, the population of shoppers at the mall is increasing at a rate of 2,000 shoppers per hour. Let's determine the rate at time 3. Fortunately, at time 3, our graph is also a line segment. It's going up 1,000 over 2. Of course, 1,000 divided by 2 is 500. At time 3, the population of shoppers in the mall is increasing at a rate of 500 shoppers per hour. The velocity of an automobile in miles per hour can be modeled by v of t. Let's first take note that velocity is measured in miles per hour. Velocity is a rate, which tells me that v of t is not a primary function. V of t is our first derivative. Let's take a look at the graph of v of t on our graphing calculator. I'll type in y equals 40 ln, and I suppose I'll have to use x plus 1. I'm going to set my window from 0 to 10, and then I'll zoom fit. I have the velocity function, so to find the velocity of the car at time 3, I need only plug in 3. I'll trace 3. At time 3, the velocity is 55.45 miles per hour. Let's find the velocity of the car at time 5. At time 5, the car is traveling 71.67 miles per hour. Now, we learned today that acceleration is the derivative of velocity, but unfortunately, at this point in calculus, we don't yet know how to get the derivative of 40 ln t plus 1. This is the velocity function, and acceleration is the derivative of velocity, so what we're really looking for is the slope of this function at x equals 3. We've already learned that we can draw a tangent line at x equals 3, but let me show you another way to determine the slope of this function when x equals 3. I'm going to bring up my calculate menu. Second, calculate, and I want to calculate the slope, or the dy dx. So I'll choose option 6, and I want to determine this when x equals 3. At time 3, the slope of this graph is 10, so the acceleration is 10, and our units is miles per hour squared. Let me find the acceleration at time 5. I'll second calculate the dy dx, or the slope, when x equals 5. At time 5, the acceleration is only 6.6 miles per hour squared. To determine if the car is speeding up or slowing down at time 3, I simply need to compare the velocity at time 3 with the acceleration at time 3. The velocity at time 3 is positive, and the acceleration at time 3 is also positive. I can conclude that the car must be speeding up, and my justification is because both the velocity and acceleration are the same sign at time 3. Time for you to go try some of these. Make sure you include your units on all of your answers.